whole course on it. You are welcome to take that. So I'm going to go a little fast and not explain everything, but if you have questions, I can wait. I can stop and explain something specifically. It's not a problem. Just ask. You can see the movie first?
Yeah.
You see that movie?
Yeah.
That movie is like all about NLP. If you haven't, you should. It's really good. And the picture of the future where basically intelligent devices are computers, are basically having natural conversations with people. Really, it's like one of the best I've ever seen. So definitely worth watching. Okay. So, can we get some lights on?
Yeah.
It's already a lot of light. Oh, okay. Good. All right. So the first thing we need to do is explain what is NLP. And I like to have a slide that basically makes it clear. NLP is not what this man does. Okay. You guys know what that is? Yeah, you know what it teaches? That's right. So, programming languages and human languages are not the same at all, right? NLP is about human language. This is about natural language. That's what the N stands for. And computational languages are very different. Now, who can tell me one difference between a computer language and a human language? Yes?
There's a ton of synonyms in human languages.
There's what I'm sorry?
A lot of synonyms
In what?
in human languages, and in computer languages, usually there's a few commands, but there's not that dynamicness of having like multiple meanings to it.
Okay. So are you familiar with this operator?
Could you slide over?
What does that mean?
Ternary.
What's that?
The ternary.
It's not a ternary. It's just the if statement.
Oh.
It's just an if statement. It just says, if this is true, that's the answer, otherwise that's the answer. Right? Different languages have it slightly differently. Right? So that's just like an if statement. That is exactly like an if statement. And there's many other things I could write that would get me the same code. I could write 3 if statements, I could write a loop that goes to 3. So those could be considered synonyms because they do the same thing. That's what synonyms are, right? They're supposed to mean the same thing. So a lot of people would say computer languages also have synonyms. Is there any other? I mean, you're getting close, but that's not exactly what we're getting. Yes.
Maybe if you take the inverse, where computer languages are deterministic, where everything means exactly one thing.
Right, that's exactly right. That's the one. That's the key, right? And even that's not 100% true in computer languages because there's this dangling else problem, if you've heard about this, right? It's like you have an if, then, and then you have an else, and then another else. Each else goes with what if, you know? And, but, you know, languages have a way of doing it. But that's exactly what it is. There is no ambiguity in computer languages by definition. Otherwise, you can't write a program, right? It's got to mean at least exactly one thing. Your compiler is going to understand just one thing, right? You might have different ways of saying that one thing. That's great, but once you write it, there's no ambiguity, and that's the biggest challenge with human languages. There's a ton of ambiguity. There is no compiler. There is no list of like all keywords. You know, everybody is just kind of just doing their best with their brain. That's what makes it really difficult and challenging. So you may have heard all these terms. They're very similar. Natural language processing, computational linguistics, almost the same as natural language processing. Most people consider it exactly the same. I don't use it because that really sounds like we're talking about computer languages, but still, it's all about human languages. Speech processing is the part of it that basically has to do with just spoken speech. Natural language processing, a lot of it, in fact, I would say most of it, is not about speech. It's about written. It's about written text, analyzing that, understanding that, being able to respond to that, summarizing that, doing things like that. Voice processing, it's also voice, doesn't necessarily have to be speech, but it's just voice. So these two basically are signal-driven analysis. And then natural language understanding. Natural language understanding and generation are considered two subparts of natural language processing. I would say 90% of the work is on natural language understanding. That is to say, once you have something written or once you have a voice, trying to understand what it says, and then having the machine do something about it, right? The natural language generation is very new. I mean, it's not new as a concept, but very little work has been done on that, right? Generation is when the machine talks back to you, when it gives you natural language. Lots of machines don't give you natural language. You can be asking for something, but I can naturally go and put a sentence into Google, and what I get is a results page that has a bunch of things ranked, but that is not an English sentence, right? Now, things like Siri, Alexa, Google Home, Cortana, things like that, the virtual assistants, which have only been popular like 2 years, you understand. Those things give you a natural response, but it's not so natural. It's not as natural as humans. And people have no problem distinguishing the fact that they're robots, right? So natural language generation has a long way to go. Corpus linguistics has to do with just reading, having a machine read lots of text that has to do with a particular author or a particular style or a particular collection, just a name collection, and then learning stuff about that. Stylistic, same thing. It's about style. It's about the way things are written, the way things are spoken, the way things are, grammar constructs that happen to be popular, like between 1920 and 1945, like that. Pragmatics is one of the most important problems, unsolved problems, I should say, and that has to do with language that is not literal. And we have a pretty good way of understanding language that is not literal. We use it all the time. We have sarcasm, we have idioms, we have all kinds of things that language is used for, but it's not literal. And so, and sometimes we even, as humans, have problems distinguishing the literal from the non-literal, or what the non-literal really means, right? And so it gets back to deep linguistics and psychology, like regular linguistics talks about that a lot. But anyway, this is very difficult for computers to handle. And then discourse analysis. This is about a series of discussions, like a back and forth, like a 10-minute discussion you might have, and what that means, and breaking that down into constituent parts of everything that could happen during that discussion. Could be a dialogue, could be just a monologue. Okay. All right. So this is this is very famous kind of layers of natural language processing. Actually, it's not even natural language processing. It's more like linguistics. So at the very core, what we have here, at the very heart of it, is sounds. So we have these speech sounds. They're not even like coherent. They're just like e, things like that, right? And understanding those things, that's called phonetics. And then you've got phonemes. Phonemes are like syllables. Think of them as syllables of words that could be put together to form words, but every one of them is a separate kind of a unit, right? It's not just a letter, but it's a different sound, it's a different phoneme. And then finally we have morphology. That's about words. So that's basically the first, usually when we do natural language processing that doesn't involve any speech processing, we jump right in over here. And we don't have to worry about the signaling and getting the signal transcribed correctly, which is still not 100% accomplished, right? And then out of words, we can make phrases and sentences which have some grammatical meaning. And then we have literal meaning of phrases and sentences, that is understanding one full sentence, like open the door, or what is the weather today, or pull up my calendar, things like that. And then finally, we have meaning in discourse. That is to say, what does it mean in this context? And that's when we get into pragmatics. That's the stuff that is non-literal, which is the hardest thing to try to work with. Okay. Most people now, these days, basically have internalized the fact that if you're talking to a device or a robot, that you kind of subconsciously don't use anything non-literal. You try to be as clear and literal as possible because that's what's been conditioned, right? And that's great because that really helps device builders not to have to deal with, people using like crazy language and stuff that's not it's not literal. But that is not as natural as if you could actually handle anything that someone says. And so a lot of work these days is going into this. So here's an example of pragmatics. Okay, this is kind of a joke, but actually there's a lot of truth to it, right? It's like people say something like quite good, and it really has nothing to do with the meaning of those two words put together. In context, like in context of being in Britain, it means different things. Like that means a bit disappointing. I would suggest means do it or prepare to justify yourself, And accidentally, by the way, means the primary purpose of this discussion, So things like that happen all the time. And when we want to discuss pragmatics, we have to get into the intent, what in linguistics they call speech act. What is the intent of what I'm trying to say? Forget about the words that I use, but what is the intent, right? For example, I could come in here and I just say, hello, or what's up, or what's going on, or, lots of different ways of saying the same thing, right? Now, if you look at the literal meaning of those things, maybe they're not exactly the same, but my intent is just to do a greeting. My intent is to do that, right? And I'm just using different words to say the same thing. So if I can find a way to use words, to find words and map them to the right intent, that helps quite a bit in trying to do natural language understanding. That's not done 100% either. Lots of work there left. Okay, so natural language processing basically is linguistics plus computers. Also, that's why it's also called computational linguistics. And there's basically two flavors of linguistics using computers. One of them is what's called rule-based, also called symbolic. This actually parallels the two flavors of AI in general: symbolic AI and statistical AI. So symbolic AI is all about logic. It's all about encoding everything into a language, like a logical language, like a Boolean expression, and then trying to do analysis on that, solving an equation. And it has tremendous advantages because what happens is that if you can get things to an exact form, then you know what the answer is because you can basically prove it. You can logically solve an equation and prove it, right? Most of AI, right up until early 2000s, most of the accomplishments of AI have been through rule-based or symbolic AI. Statistical AI kind of was a thing that people messed with for a long time. There was a lot you could do with it, but it really wasn't practical until very, very recently, like in the mid-2000s. And then it all of a sudden became practical, and then everybody used it. Okay? And now it's basically taking over. All machine learning that we're talking about is statistical AI. Because what it is that is associating certain features or certain attributes of an object with a particular label, right? That's really all machine learning is, okay? And in natural language processing, both of these are really important, but they have severe trade-offs, right? This means you can actually get really precise output that is correct, okay? The price you pay is that you understand very little. A very small slice of what people speak is actually correct grammar. And converting that into a logical equation is not very easy. What you have to do, most systems that do that, they basically have a subset of grammar, a very kind of reduced set of rules that it is not the entire English language, it's just a very narrow set of English language, and that's the thing they understand, not the full English language. Okay? So that's basically like learning, I mean, at some point it becomes basically learning the commands that you need to know to talk to a machine or a virtual assistant. It only understands things in a certain format, certain grammar, with only some words, right? But once you do it that way, it's awesome because it can figure out the answer once it knows exactly what you're saying. Okay? This, on the other hand, is very different. This one, the good thing about it is that it can take anything. Twitter is not even English. I mean, there's no rhyme or reason to it, basically. There's just so much out there. And statistical approach doesn't care. Neural nets don't care. Bayesian statistics, they don't care. You know, you get like a spam email that's like written in like Russia or something, and it doesn't really make any kind of English sense. It doesn't matter. It'll work with it. Okay. Of course, the trade-off here is that it'll work with anything, but that its output is not as precise. Okay. So this is all about prediction. So it's making a guess of what this is. This is all about solving equations, but then the only things you can solve are very few things that the system knows about. And scaling this so that you just have enough rules to handle everything is just not practical. That's what's been realized in the past 20 years. Okay? So there is a lot happening. There's the trend that is driving this whole thing is that there is a lot of information that's coming online. There is a lot of conversational agents that are coming that are taking advantage of that information. Tons of information is being generated for the first time in human history. All of it is machine readable because it's like already in a digital format than it used to be the case at the very beginning. And then human-to-human communication is increasingly mediated by machines. Like you're talking over Skype or you're talking over Slack. And what that really means is that there's that many more examples for a machine if they want to gather everything to learn from it. All these companies are doing that. Every single company is gathering everything you say, anything that they can, because the more examples you have, the better your statistical prediction, okay? So Gmail is reading all your email. Facebook is reading all your chats, right? I'm not saying that they're gonna like figure out who you are and like come to your house or something like that, which actually has happened. But what I'm saying is that a machine is going to gather all the samples and then learn from it, learn from the language samples so that it knows how to better expect things in the future. Okay. So obviously a ton of industry work being done here. Very, very cutting edge area. Things like auto translate is very important. You can go to Google now, for example, and then get any page translated. But if you pay attention, if you know both languages, or even if you just read in English, you know it's not that good, right? And that's literally the trade-off. Google is doing it in a statistical way. This is statistical inference. You're not going to get good grammar. You're not going to get always cohesion. If somebody in that language were to write the thing from scratch, it isn't going to sound like what Google's translation is. But at least it's something. It's much better than not having anything, right? And we're very, very close to this being very ubiquitous. That is to say, I speak and something translates live to a different language. There's already some prototype systems out there that do that. I feel like that's going to be a solved problem happening. And if it can do English to another language and another language back to English, then it can also do English to English and change the style of the way you say things, which is very interesting too. It's getting a lot of people are looking into that now. Okay, so web QA, that's like asking a question. So that's close to what you guys are talking about doing with your project now. What's the population of Boulder? There's going to be a response that's going to have the answer for me. Now, it's not exactly an English sentence that can tell me the answer, but in this particular case, it's not very hard to make that English sentence. If I just have this number, I can seriously do that, right? But what web QA is basically doing is, it's finding the page that has the answer, and it's not yet smart enough to go parse that page, find the answer, and put it in a generation system, and then give you the answer as like Google Home or Alexa or Cortana, those systems. They can do that now for limited set of things, and I think the Google one can probably do the most, but not for everything. And there's a lot of systems out there that are looking at intent as well, and trying to figure out what the intent is because of the different ways you put something and different kind of hints that people have. That it's very difficult for computers to understand, just because, I mean, just if you think about it, we use so much crazy language that is not literal. Like if I came back here, like let's say if I was half an hour late, right, to this meeting, and I come into you and I say, "Hi everybody, thank you. Sorry I was a bit late." Okay, nobody would bat an eyelash for me saying that. But if a computer had to understand a bit, that means little. Half an hour is a long time, right? It's part of the language for me to like underplay that, and everybody knows that. But it's not part of the. But no one's taught the computer that that's the case, right? So in like a lot of negotiations, people use this language just to have a better relationship or like make people feel better, and all these things are used all the time. And it would be nice if you could turn off the light. That's a statement. That's not a question. So if you ask that computer if a computer were to interpret that literally, the answer would be yes, it would be nice, and then it wouldn't do anything else, right? But I'm asking that. I'm not asking. I'm making that statement. My intent is to get you to turn off the light, right? But what I'm saying doesn't actually ask you to do that, right? So that's the challenges. Okay, this is from a book called LTK that I teach in my 482 class. Well, I will teach you my 482 class because I haven't yet taught a 482 class. The first one is in the fall. And so it's a very classic kind of pipeline of how to understand and generate language. So if you start over here, that's speech analysis, that's like signals and everything. Then you get into morphological and lexical analysis. That has distinguishing words from each other and understanding a series of words that was in. This is basically transcription, right? This part of it, for like a lot of systems that do that for you, they can take advantage, but you don't have to do that. That just gives you words. This gives you a parse. That is to say, it has to, coming in and then as an English sentence, it'll try to parse it so that it knows that it's a complete grammatical sentence, and then that has a hope of, not a guarantee, but a hope of being able to associate that with some actual thing that you're asking, okay? But the first step is to parse the sentence in that process. And then you do some contextual reasoning. This is just like some ambiguous things that you don't know about, you try to fill it in. We as humans, very great at doing that. We don't have to do that at all. Like, we don't consider like people something that people say in a complete vacuum. What we do is we know the context. If I were to say, let us start our engines, okay? And then right here, you would think that, hey, let's do some actual NLP work, right? Something like that. But if I were to say that out there, that might mean to someone else in a different context, it might mean, yes, turn on your car, or all kinds of other things, right? So that's the contextual reasoning. And then, what happens over here is, you're going to be able to put this into some kind of application reasoning. Now, classically, this has been the symbolic logic. So everything down here ends up being like the first order logic. And in first order logic, or maybe even second order, then you can do some reasoning. Then you can do some resolution. You can do things like if A is B and B is C, then A must be C, stuff like that on there. And then you would form a response, but the response first will be utterance planning. That is to say, well, what am I going to say first, and then second, and then third? And then here's I'm going to put it together in form of an actual sentence. And then here's I'm going to fix the actual words that match that sentence. For example, if it's past tense, I'm going to make the words past tense, things like that. And then finally, I'm going to vocalize it. Okay? So this is the classic pipeline. There are some ways of basically jumping from here to here. Especially if your NLG pipeline is not very sophisticated. That is to say, you're not actually producing novel sentences every time. You maybe have like a series of 10 or 15 templates that you simply fill in. And so basically it's possible to go from here, or maybe even from here, straight to here, and bypass this whole thing, okay? And this is actually the approach that we're taking in my class for this assistant that has to do with answering questions about the department, okay? It certainly cuts down a lot of work and makes it possible to do that in a quarter. Okay, so yeah, some major topics: morphology, shape of words, syntax, the words themselves, semantics, what do the words mean, and then discourse, put them together in like a long conversation, and then generation, have the machine create them for you. Some very big applications that are still open: speech processing, still open; vocalization, getting better, but still problematic, right? You realize how much money this would save people if vocalization would work. You guys play video games? Okay. You know how there's like voice actors for all those characters in video games. All those characters have voice actors. What does that mean? That means the lines have to be written ahead of time, which means the stories can't really be all that dynamic. There's AI that can handle much better dynamic systems. Like if you put an AI in a game, AI is an NPC. And that NPC could be much smarter about things, and it could handle things on its own and have its own little brain inside and do things. But the problem is, there is only certain things it could say because of this vocalization problem. So therefore, it can't be that smart inside of games, right? Because if it does something else and it wants to say something else, that line wasn't recorded by the voice actor before, so it's stuck. So lots of things can be a lot smarter if vocalization works. Okay? The problem with vocalization is that, I mean, it's working now, we have it, it's getting much better, but it's kind of like, it sounds a lot like a robot. It's very much monotone, and the vocabulary is limited and everything. And there's a lot of good work being done into changing that to having stress and feelings and slowing it down, speeding it up, and just all these things so that it sounds more human. And once that gets done, I feel like it's a huge revolution with a lot of systems that's out there, right? I mean, vocalizations that we have now are basically on the order of Siri and Alexa. Very good, but no one could mistake that for actual people, right? Question answering, very much a relevant topic. Everybody's talking about it. Everybody needs to be able to do it correctly. You may probably, I don't know when you did that tech support or had to call in for tech support or visit a tech support website. Almost all of them these days have a pop-up conversational agent that shows up. And at least for the first few parts of the conversation, it's robot driven. And then it sort of backs it down to a human, and then the human can take over from there. But tremendous cost savings right there, just to figure out, which expert they have to call so that they can do the work, right? Conversational agent. Automatic summarization, extremely important and very much open problem. Very little work has been done in the last 20, 25 years on that. So I want to read like a 400-page, filing for the federal election commission or some kind of like tax report or something, and I just want to know 2 paragraphs of what it says. I don't want to read the whole thing. I want to see the summary. Okay, very difficult to do that. Systems are working on it. Things are happening, but nowhere near solved. Right? Machine translation, we talked about that. It's very close, but it doesn't sound as human. Computational stylistics, also just scratching the surface. Okay. So now let's talk about all of the knowledge that is needed to actually do any processing. The part at the end where you actually do processing, we as humans do this because we have a brain and we have like a lifetime of experiences that we can bring into something to understand what that meant, what that sentence says. And this part really hasn't been duplicated in computers yet, right? You can't have a computer that has had a lifetime of experiences yet. I feel like you can probably fake it at some point pretty soon. That can answer the question, right? So, so the best we can do is take the input and code it in some kind of, this is in this case first order logic, that we can do processing with, rules-based processing. And so this is what you do with first order logic. Like I have 2 brothers. Basically things become functions. Brother, possession, I have 2 brothers, like that. Rabbit is furry. I love rabbit. Possession, I have rabbit, like that. Okay? And basically the whole thing becomes like a big logical equation that you get to solve. Again, very few things can happen this way just because you have to have correct mapping from this to this, and that's really hard. But what about this? Let's look at this. When I banked on banking. Okay, I could say that it could be like a funny line at a TED Talk or something like that, and people could know what I'm saying, but the machine will be totally confused, right? I'm being dogged by a dog carrying a dog. Okay, there's a definition of a dog that says it's a mechanical device used for gripping or holding. Okay, there's like. And then look at this. I got a new car today. That's nice. But I totally destroyed the clutch. That's real nice. Okay. How can a computer understand this is literal, this is sarcasm? Very, very difficult problem. Okay. So I don't know if you guys seen this.
Squanch, hey! Your language has the word squanch in it a lot. Doesn't that become tedious and worn out like the Smurf thing?
Beth, squanchy culture is more contextual than literal. You just say what's in your squanch and people understand.
Oh, okay. I squanch my family. Yeah, I do. I squanch my family.
Stop saying it, gross! Come on in, guys. The guests are having cock squanches. Where am I?
We're at a wedding. Go change.
So yeah, ambiguity. One of the fundamental problems. I made her duck, for example. There's at least 5 different meanings for that, right? Did someone figure out? Did you raise your hand to figure out what the 5 meanings are? Maybe just give me one. Yeah.
You prepared her a duck dish.
Prepared the dish. Yes. What else?
I told her to duck her.
That's right. You told her to lower her body, right? You caused her to lower her body. What else? Yeah, that's fine. What else? Yeah,
You caught her duck doing like a nefarious act. So like police, like we made him.
Oh, yeah.
I made her duck. You caught it.
you made her duck.
I
Oh
think
wow,
that-
I didn't even think about that. I don't think that's one of the 5 I even had in mind.
We got 6.
But yeah, so yeah. So what you mean is like you discovered
Yeah.
the ducking, right? Okay. Anything else?
Can you add a comma in there?
What's that?
Can you add a comma?
You can't add a comma. I mean, it's ambiguous enough as it is. Yeah. Okay, so let's look at the ones that I have. So yes, I cooked her waterfall. I created, I cooked, right? And then I cooked the waterfall that belonged to her. I made her duck, not my duck, her duck. That's the one I cooked, right? And that's a different kind of ambiguity between the two ways. One of them is the ambiguity on duck, the other one is the ambiguity on her, and then obviously the ambiguity on me. I created like a plastic duck, we said that. I caused her to quickly lower her body, that's like, and then I waved the magic wand and turned her into a duck, right? That's also one. So, and a machine is supposed to know the difference between these 5 things, right? The question is, how do you know the difference between these 5 things? Like, which one of the 5 is it going to be, or 6? Yeah, so what are you really doing, like, if you think about it? Yeah, it's contextual, true, but what does that mean, like? Yeah.
I have like prior knowledge of something.
Of
The context.
this conversation, right? So so what you're doing is, you figured out that this conversation, as it's happening, has a certain vocabulary associated with it, and some of these, or I should say, vocabulary and senses, like a sense of the word, associated with it. And some of these things are going to be outside of that, and some of these things are going to be inside. And you've decided that if we're talking about like a dinner situation, then I'm not talking about her lowering her body, right? So that's what you did in your head. And so we need to get computers to do that too. Much easier said than done, but that's the challenge. And then there is, but let's see how we can, as programmers, try to figure out the difference between the two. I mean, we already have one big hint in that, yeah, there's certain things associated with this context. If I know the context is cooking, then I know all the cooking words that go with it, and duck probably is the thing because that's something people cook, that goes in here, right? But how can a machine help me? Well, there's a lexical category, that duck. If it's cooking, well, it's going to be a noun. If it is lowering her body, that is a verb. So if I know which one of the two it is, that cuts down on my choices significantly, right? And then this over here, the lexical category, there is this her can be possessive or dative. If it's possessive, that means it's of her. And if it's dative, that means it's for her, right? If I had a way of figuring out which her we're talking about, that would cut down as well, yeah.
Are you almost saying that this process is kind of like using processes of elimination to just kind of...
That's exactly what I'm saying. That's exactly what I'm saying. In fact, it's even worse than the process of elimination. It's process of narrowing down and then taking the best guess you have. Because that's basically what we do in machine learning. Is you just take the best guess. And sometimes you're going to be wrong, but at least the ones that support the most evidence, you're going to go with that choice. Okay? And, and last one, there's a lexical semantic, make, or it can be create, or it can be cook. And if I know which one of the two it is, then it would help me narrow down one of the 5 things as well. So, transitive verb, or ditransitive verb, okay? Are there ways that I can figure out just between transitive verb and ditransitive verb? How do I even know how to label something as a noun versus a verb? How do I even know all that stuff? Well, Luckily, there are ways. There are ways. They're not going to be 100% accurate, but there are ways because in machine learning, and this is why NLP and machine learning are really, really like tightly coupled. Okay, they're both kind of inheriting from AI, but NLP is machine learning is an integral part of NLP. The two kind of won't exist without each other, right? And machine learning is the thing we need to use to make those small decisions. And then we can use NLP to make the bigger decisions. And actually, we can use machine learning there as well to make the bigger decisions, okay? So, luckily for us, a whole bunch of smart people in the 70s took like large corpora of text and then by hand sat there like linguists and basically tagged all the words to be like, this is a verb, this is a noun, this is, and this is like, these are standard corpora, like the Brown corpus is one of the most famous ones. It has like plays, and it has like essays, and it has, like newsreels, and another one is called ABC corpus. It's like a lot like newscasting and things like that. Lots of different kinds of writing. People sat down and did all this by hand. Everything that you can tag about the word, is it past tense? What sense is it? What is the actual meaning in this context? What is all the linguistic features about it? Like a lot of work, right? And what we've basically been doing since is we've been using all that stuff in the computer to make an inference. To be like, that's our training set. Now we're going to get like a new language we haven't seen before, and we're going to predict all that stuff on new language we haven't seen. Question?
Are these like data sets readily available?
They're all available, and most of the important historical ones are in the package that we use in 482 called NLTK, already bundled into it. Actually, you have to separately request each of them because they come together to like maybe a couple hundred gigs. But when you install the basic package, you have a choice of also downloading the corpora, and then you can do that. Okay, yeah.
Are those data sets all from the 1970s?
Most of them are from 70s, maybe some in the 80s. The thing is, there really hasn't been a major need to do something like that from scratch since that time. Although some people say it should be. Because we're so good now on trying to predict with that stuff that if we're going to do something like that in the future, that we're just going to use some of that stuff and then maybe double check it with the human, but don't have to rederive it from human perspective. And it's very expensive too. So it hasn't been done in decades. Yes.
If you had one of the corpuses, are they too large to use like locally? Would you have to have
No,
them?
not at all. Oh. No, the Brown corpus is totally useful. I mean, we use it in class all the time. You can download it, you can learn from it, you can write your own part of speech tagger. And actually, all the ones that you use anyway, like even if all the, all of the library API calls that you can make depending on the package that you have, they are also trained on that. So you can write your own, or you can just use one of the ones that's been trained on that. The most parsing too. Parsing is one of the most computationally intensive activities. How do you parse? Like how if I said I made a file, like that's 5 different parses, right? When I said 5 different ways of saying that. And so the Stanford parser, for example, even lets you learn, which is considered the best parser, even lets you learn from the data that you give it. And then it has some predefined like New York Times data that it can learn from. And then parse your sentence using that training set. Or you can provide it your own training set. And then it'll run that training set, build the model, and then predict on this stuff. And then there's this whole new level of phonetics, okay? Phonetics is a serious problem because literally converting sound is also ambiguous, right? I ate her duck sounds exactly like I made her duck, right? It sounds exactly the same. So if you have a system that's supposed to listen and put down words, transcribe, all these are possible. And in fact, most good transcription systems also use that same corpus to try to disambiguate that, well, this is probably not very likely, right? This is not even grammatical, like that. And then to cut down on the choices, right? Still, not an exact science. So, machine translation, can anyone read this? No? Okay, machine translation, especially for written text, benefits greatly from machine learning because it can work on co-occurrence, right? So probably the best machine translation system out there is Google's. That's the most famous one, and it basically works if you go from written text to written text. That is right. It basically works not by really understanding the whole sentence and then putting it into like a first order logic and then generating the Chinese on the other end, right? That would be very difficult and it would be very, very expensive and it doesn't scale up at all. It basically does it by finding lots of pages that actually have the Chinese and the English on the same page. And then it just learns from them, right? So, like this. Like let's say you wanted to translate these things, okay? Well, all I would have to give you is a Chinese menu, and you could do it. Because you would look at, for example, this symbol co-occurs all the time with the word wonton. Whenever there's wonton, there's this. That must mean wonton, right? And then further, chicken. This symbol shows up whenever there's chicken. So I know that there's an association at least between that and chicken. And I could go through and do this like over and over again. And if I'm Google, I have access to the entire internet. There is so much out there that I could learn from and actually get it reasonably correct. Of course, it's not always 100% correct. For example, here we call this soup, but for some reason it doesn't actually have the symbol for the character for soup that everything else has, like maybe some kind of slightly different soup that we don't have in English. German has the same problem, like lots of different words that don't really exist in English. Somebody had to make a judgment call of what to translate it to, and that happens, right? So because it's statistical, it's gonna be imprecise, but at least there is a chance that you could do a large number of inputs. Questions? Okay. So, all right, now getting down to how do we actually do this? How do we actually use computational means to solve these problems? So we need word level processing, we need syntactic processing, we need lexical and compositional semantic processing, we need discourse processing, we need dialogue structure. And this is my kind of ongoing contribution to this. If you remember, we had that basic pipeline that basically went from sound all the way to symbolic representation back to sound, right? Here, I'm throwing in machine learning at many parts of that same pipeline. And this is very useful in case you don't want to go all the way to the end, which is going to be very difficult to do, especially because the symbolic representation doesn't have that much coverage. You have to have lots of rules, and it's not scalable to do that. So what I'm saying is, at the very beginning, first of all, you have speech-to-text processing. This is going to come into your project, right? So somehow you're going to get audio into text. And then that becomes text acquisition. You either get it from audio, or you get it from like Word docs, or libraries, or whatever else is out there, scraping websites. That's a distinct part because it needs to be done. And it needs to be cleaned up and make sure that it's like correct English and all that stuff, right? And then from here, you unformat it. What you can do is generate some metadata. So without even looking at it, you can generate some data, like this came from a website. So I know that association. This came from a YouTube video. This other thing came from this place. And you can actually do some work just with that. But most of the time what we want to do is, the first step in anything is tokenization. Who knows what tokenization is? Yes. No. Yeah.
You break up your data into like labelable chunks, like tokens.
You break up your data into chunks, not labelable yet, just chunks, right? Sorry. The chunks you're interested in depends on the part of the process you're in. But where is okay. So most of the time we're talking about, it says WSD, that stands for words, sentences, and paragraphs. Okay, I need to tell those things apart from each other. Most of the time I'm talking about words. So if I were to say something like, my name is Fuad, right? I need to get the words out. That's called tokenization. Get my and name and is and Fuad. Now, you guys know how to do that? In Python?
Split.
How would you do that? Split by? Okay, well what about this last one? Remove the period. Okay, but what if it was an exclamation mark?
Import RE.
Okay, all right.
Other expressions, take out.
Take out. So you basically have to sit there and come up with all the possible things it could be. Could be it. I could write here. I could have a colon. All these things. And then I want a sentence disambiguated too. Like, my name is Fuad, I am a professor. How do I know that one sentence starts and the other sentence ends?
Curious.
Okay. So, but what if I said, my name is Fuad, and I am a PhD holder. PhD has 2 dots in it.
Space.
Dot follow.
Right. Okay.
Regular
So,
Just a dot. Oh, shoot.
right? And then paragraphs too. I need to figure out like one paragraph from another paragraph. And you know, that's usually like something like look at when there is two white lines. But if I were to two new lines, right? Basically 2 of these, split based on this, usually I get a paragraph. But if I were to scrape something off the web, then new lines don't mean the same thing on the web. It's like break points or like paragraph tags. That would be different. Okay. So this is something that all of you could probably write, but it's not trivial. You're gonna have to think about all of the different possibilities that exist here. Okay. And there are very good libraries out there that do that work for you, that you can use. So the main library that I'm talking about is NLTK. You can go to nltk.org. Another one is called CSAI. Both of them are really good. This one is faster in some cases, is newer, and does the work faster, does better parsing. This one has a lot more coverage, does a lot of different things. 5 to 10 different algorithms per item are documented, and has all that data that I said about like Brown corpus and ABC corpus and all those tag corpora. Okay? So tokenization must be done, and you have to, you are very well advised to use one of the existing systems, because those systems, all they have is, they have all of the examples that you just talked about. They have all of the possibilities. They have the exclamation marks and all that stuff in there, and they just run a bunch of rules that somebody come up with a long time ago, and then they can tokenize it really well. Tokenization is an easy problem, but there is like lots of cases here, right? So word, sentence, and paragraph tokenization can be done, and then right after that, stem and lemmatization, right? Who knows what stemming is? So a stemming, both of these are ways let me back up just a little bit, because we're going down here to machine learning. I'm trying to tell you why. So, in machine learning, one of the things that's very important is a distance or an association between two different objects, right? Like if I were to ask a question about the library, and then I have an answer that answers something about the library, I want to be able to say those things belong together, right? But how do they belong together? Well, the only kind of game I have to associate those two together is like, well, do they contain the same words, right? So if there's lots of library words in this question, lots of library words in that answer, those things must naturally belong together. And I can classify them together. That's what machine learning does, right? But machine learning works on, in this case, distinct attributes like words. But words, they could be really close together, but not spelled the same at all, right? I could say engineer or engineering. And if I simply just based on token try to match those things up, well, they're not the same. So if my question has engineer, my answer has engineering, like where would an engineer be studying? Answer, engineering building. You know, where would an engineer be studying? Answer, in the engineering building, right? And the two words aren't the same, but I know that there is some similarity that they have. I know the root word is the same. I know they come from the same idea of engineer. Both of them mean very similar things, right? So stemming is a way of altering the word so that it has more in common with other versions of itself, right? So engineer and engineering, both of them could be made into engine, and then now I know that this has engine and that has engine, and I could find a similarity, right? Of course, if I'm doing some kind of semantic analysis where I want to know what the thing actually means, then I wouldn't want to lose the correct shape of the word, because I want to know that engineering is a verb, for example, right? But if all I'm doing is trying to associate one text with another text, find a distance between them, this is really helpful. So stemming is a very crude set of rules that goes through and basically chops off like word suffixes and prefixes and things like that in English. And so that the words kind of have more overlap, they become very similar, okay? For example, one rule, and there's different algorithms for this, 6, 7 different algorithms of stemming algorithms. All of them are available in LTD, you just choose one and run it. And for example, one would say, if the word has at least 2 syllables and it ends in ER, then change it to that same word and just chop off the ER, okay? So I could be like, crazy, crazier, right? Crazy and crazier would basically end up with the same craze, right? Because IER, I'm going to chop off the ER, right? But the word like beer, which only has 1 syllable, I wouldn't do that because that's not what I want, right? The ER in beer doesn't have the same function as the ER in crazier. And so I don't want to run it there. So that's why that syllable, the rule says, make sure it's at least 2 syllables. Bunch of rules like that. ING, ED, S for plurals, all these things, right? The problem with stemming is that, the good thing about stemming is that it works really well, like collapses lots of words together. The problem is that it's kind of dumb. Like, it doesn't understand that these words have meaning behind it. All it does is run these rules, right? There's another version called lemmatization, which is actually much slower, but it actually doesn't look up on the word in a dictionary. It finds the root word and then changes the word to the root word. The root word is guaranteed to be English, not like crazy with an I, and then that's not really English. And then if everything collapses to its own root words, then that's another way of increasing what they have in common so that you can make a distance association, right? So the other thing you can do is part of speech tagging. Part of speech tagging is a way of saying, give me the nouns, give me the verbs, what word here is the adjective, what word here is the adverb, all that. goes through one at a time, figures out what the words, what the parts of the speech is. How does it do that, you might ask? Well, it's because it has all that statistical info from the corpora that was tagged by hand. And it knows, for example, that a word, like say house, appearing after a certain other word that's already been tagged as verb, then that one must be a noun, like that, because they've seen so much examples in the past, right? Goes through and does that. It's not 100% accurate, but it's pretty good. It's pretty good, like maybe 95 to 98% accurate. And then considering the fact that you're gonna get words that it doesn't know, because names and things like that. I mean, it knows proper nouns from spelling, capitalization and things, but it doesn't know everything. Considering there's a lot of that around, 95 to 98 is really good, right? And then what you can do is do phrase recognition, a series of words together that have a special meaning. Name entity recognition, things like North by Northwest is a festival. I don't want to say like north is a direction and by is like a determiner and northwest is another direction. Like, I don't want to do that. The whole thing is just one big proper noun. And that's what the name entity recognition does for me. It's extremely useful for things like Twitter analysis and stuff like, name of a company and things like that. Like, because those things, they could have linguistic meanings when you have a name, right? So it's like Apple. Like, if I don't say anything to the machine about Apple, it's going to think I'm talking about a fruit, right? But if I have name entity recognition, it's going to know that that's a company. And then sentiment tagging. That is based on the words that are used, based on the connotations of those words, and those are just strictly based on what we've seen in the past. Like, whenever the word sucks is used, that means it's bad, -1. Whenever the word great is used, that means it's good, +1, right? Put all that into the whole phrase, find out that the whole thing is +1 or -1 or good or bad, like that. That's sentiment, okay? And then we get down here to word sense disambiguation, which is probably one of the hardest problems here. And that is nowhere near solved, right? Word sense disambiguation means what sense of the word am I talking about? When I say dog, am I talking about a hot dog? Or am I talking about an animal? Or am I talking about that iron thing? Or am I talking about an ugly person, which apparently is another synonym for dog, right? Which one am I talking about? And it's a very difficult thing. There's a very good corpus called the WordNet. WordNet is bundled in LTK. And WordNet is just like a big structural representation of all the words in the English language. Not all the words, like not even close to all the words, but a lot of the words that we use. And looking at words in WordNet can give you the possible senses that they belong to. The whole thing is organized around sets of senses, right? And so you can get 5 senses, 6 senses out of WordNet. And the other cool thing that WordNet does, it gives you what sense is the most common. Like for dog, it's going to be the animal, right? And if you just go with the most common sense, you're going to be right about 70% of the time, which is pretty good. If you use the latest, most sophisticated machine learning algorithm to try to decipher based on data and theory and statistics how to do the sense disambiguation, you're going to be right maybe about 73% of the time. So it's a long way to go to solve that problem, right? And it's very crucial. And then getting into non-literal pragmatic tagging, which is also very good. What's irony, what's sarcasm, things like that. Anyway. So here's some resources I was telling you about. For web mining, I would highly recommend Beautiful Soup 4. Lots of the data that we have is on the web. All the data that we're using for the virtual assistant project is going to be on the web. So we need to know how to scrape the web and how to get the data out, and also how to get rid of things we don't need. Like lots of websites have crazy extra HTML in them just because these days, websites aren't written by humans anymore, right? Those websites you go to, like a Cal Poly website, that's put together by a script. The menu is called from somewhere else, the sidebar, the footer, everything, and then the core part of the website is from a database, and it's all put together on the fly for you whenever your browser makes the access. That means there's a ton of HTML that's like really ugly to look at. And so to get the information out of the website, you're gonna have to figure out all the parts that are irrelevant and go for the parts that are relevant. Be able to take it, take out the tags, parse it, turn it back into English. That's a very good tool, the beautiful soup. And then the NLP packages, as I said, NLTK or Spacey. WordNet is bundled in NLTK. It's very useful. It's that hierarchical thing that I told you. Not only can it do senses, but the cool thing is, once you know the sense of a word, you can get a distance from each other. There's a distance between a dog and a cat, like 0.2 or something. Distance between them, and then usually what happens is that distance between a dog and a cat is going to be much smaller than a distance between dog and, say, philosophy, right? Any two words can have a distance, and the way it does it is kind of this hierarchy of where things belong, kind of like object-oriented, right? And dog and a cat, well, at some point they're going to have very soon they're going to have a common ancestor that's like says pets or house pets or companion animals, something like that. But dog and philosophy are not going to have a common ancestor for a very long time. Based on that, it figures out a distance. It's actually different formulas to get a distance. You get that. The Stanford parsers tools are available. The biggest problem I have with this is that it's in Java. I really don't like Java. Okay. And then ConceptNet is pretty cool reasoning system. I haven't worked with it for a few years, but it's out there. Like it knows the concept of gravity, or like the concept of something can hide behind something else, and then it's actually pretty cool to look at. If you want to do some deep understanding, something like that is necessary. CMU Sphinx is probably the best speech-to-text open source system that exists, and it's really bad. It's just, there is a huge gap between open source speech-to-text and commercial speech-to-text, mainly because it's all informed by all the data that the companies have that you don't have access to. Companies like Amazon, companies like Google, they have all the source data, and that makes it a much better system. So some of this stuff is included in NLTK. IBM Alchemy is a decent named entity recognizer that you can just get the API and use. It'll give you like a numeric score between like -1 and +1 about how happy or sad the entity is. These actually have more than one dimension. NumPy and Pandas are used for just Python. And then TensorFlow, Keras, and Scikit-learn are used for the machine learning libraries that they have. Actually, there's a bunch of machine learning libraries in NLTK as well. It has its own naive-based classifier, it has its own decision tree classifier. These are better, but that can actually get you going for something small. Okay, and this is what I'm going to cover in my course if you were to take it. 482 is going to be offered in fall and winter, and 582 is going to be offered in spring. And so we're going to go through all the current issues, and then things that you really need if you want to take the 482 class: algorithms, AI, data mining, and then a lot of good, basically English skills, because that's a part of it. Okay? So, all right, let me stop here. There's a little more on this, but I'll stop here. And then I will briefly talk about the project, which we're calling Statia, Cal Poly Statistical and Computer Science Information Agents. And maybe go over this a little bit. So this is the main architecture for the project as we have it in the 466 class. And yours, the goals of the project are very similar from what I understand from GD, but you don't have to use this, or you can go any way you want. But let me tell you what we have in mind, okay? So it works like this. There's a thing called data sustainer, and that is a system that goes out and collects the data and puts it into the database, right? And that needs to run periodically on its own, completely separate from everybody else, right? For example, one of the bigger questions is going to be like, tell me Professor Kashmut's office hours. and Professor Koshwood's office location, room number, building, all that stuff, right? And there's probably a table out there in one of the department websites that has Koshwood, office hours, office location, all that stuff in there, right? And what we need to do is read that table, parse it using Beautiful Soup 4, put it into one or more of our own tables into the database, right? We don't have to do it this way, but it's the only practical way, okay? The other way to do it is to wait for the question, and based on what the question is, at that moment, go parse the website, get the answer, and return the question, okay? That'll probably be okay for what we have here, especially if we know the website ahead of time, right? At least we can make a good guess at which website the answer is. But that will not work in real life, because in real life, that stuff takes way too long, okay? Google doesn't go search the web immediately after you type your question. It has already crawled the whole web like 2 weeks ago and put that in its databases. And what you're really doing is just doing a simple lookup on its databases with just a little more processing. And that's why you get the answer so fast. It's not going to search the whole web on the fly. That's crazy, right? So that's what we need to do. This is gonna read all of the websites that you ahead of time realize, not even just websites, any sources you have, might be databases or whatever, text files, anything that has the answers in it. And you're gonna crawl it, and you're gonna put it into a database that you're gonna design yourself about, what tables go where. Like there's gonna be a table of professors, there's gonna be a table of classes, there's gonna be a table like of buildings, there's gonna be a table of staff, all that stuff, right? And it needs to run periodically on its own, which is really nice, because the other thing that happens in real life is that your source material could actually disappear on you. Like that site could be down, or more likely, the site could now be reskinned. And it's the same data, but the internal DOM elements are different now. And so the thing that actually parses the data to get the information out is going to break. But hopefully you will know that as soon as that happens, and then you can go change your process to get that done. Meantime, you have the data from yesterday if you run this every day, And then you're also responsible when things change, because you don't want to have stale information. So this is really important, because a lot of these systems, if you don't do this, they're going to be useless after a couple weeks after you finish with them, because the data will change, and then now all the questions are wrong. Yeah.
So this might be a little bit more computationally expensive.
Yeah.
But are there parsers that actually take a screenshot and review the page hierarchically like a human? Because there is like
you don't need a screenshot. I mean, you can hierarchically review it through the DOM object.
But now with like CSS grid, sometimes it's out of order. So
That's true.
Sometimes it's a little bit more difficult to review it as like an HTML script. So
Right.
it's easier to just.
I disagree that it's easier to visually process. First of all, the visual part of it could all be done in CSS, and it will be very radically different, even though the HTML is exactly the same. So what you want is to make sure that DOM is exactly where you expected it from last time. It's the internals that matter. The screenshot might be nice to have for display purposes for somebody to look at, but I wouldn't make any kind of visual image recognition or anything like that. That would be futility in my opinion. So yeah, but I don't think it's gonna work. Yeah. It's too crazy. What I would do is I would have a test where if something that you know has to be at a certain place, you double check to see if it's there. And if it's not, you kind of raise an alarm that says, oh, something has changed, the structure has changed, this page has changed, and things are different. If you do it right, it could be very much robust. That it could have some kind of robustness in that, like maybe just like the menu system will change, or maybe just like the logo will change on the website, but that maybe the part that you're interested in is still going to be the same. And if you write the system robust enough, you should be able to get it. Yeah. That's the data sustainer. Then what we do, this is the main part, the chat interface. Now for my class, I told them, this is, you guys are going to do this completely differently how we like to do it. But for my class, they have to do two things. They have to have a command line interface to this chat, basically a Python program running, and I'm typing in right at the command line, and then they give me the answer, okay? And then they have to have one alternative interface. So the alternative interface could be email, could be Twitter, could be Amazon Alexa, could be Slack bot, could be Facebook chat bot, all those things. And they have to go figure out which one they want, okay? But the brain is exactly the same. The interface shouldn't make any difference whatsoever. So you get the query from the person that says like, hey, I want to know, like, you know, who's teaching AI on Tuesdays, like that, things like that. And then the query parser goes through and does a lot of that pre-processing stuff that I told you about, like tokenization, word sense disambiguation, all that stuff. Then you're going to find the relevance detector. Now this is the part where I'm prescribing a little bit for my class because we only have 3 weeks to do this in that class, how it's going to be done. What I'm saying is, we're, as the class, people are getting into groups and every group does something specifically different. Like one group is about professors, one group is about classes, one group is about like clubs, things like that, right? And every group is supposed to come up with 120 questions, example questions that they think is going to be asked about their particular area. And then we're going to throw all that in the database, okay? And then we're going to generify it. So for example, whenever there is a professor's name, we're going to change it to just bracket professor. Whenever there is a building name, we're going to change it to just building. Whenever there is like a day of the week, we're going to change it to day of the week, like that, right? So what we're going to get is a whole bunch, 120 from each team, like maybe 1,000 different questions that are in generic form, right? That are tagged for which of the groups they belong to. Like this is a question about professors, this is a question about courses, right? And they're all going to be in here. And what I'm asking them to do is take the query, run it through the same process of generifying. Like if you see a professor's name, change it to just bracket professor, right? And then find out which query you already know about is closest to what you have. And once you find that, then presumably you know how to get the answer to. Because once you have a query, like once you have the 120 in there, you presumably would have built up a table here. For example, if I say, where is Professor Koshmood's office? Okay. The first thing, so this presumably would be one of my 120 questions. And then what I'm going to do is change it to where is Professor Brackett's office, right? And then to answer the question, I'm going to have a table that has professor in one column, office in the other column. And so no matter what professor I get, all I have to do is look up the professor and then go across to the next column, and that will be the office. And that's my answer, right? And so knowing that, I'm going to have my data system fill a table like that. And then when somebody comes up with a question, and it's very similar to what I just asked, where is Professor Koshmood's office? Somebody else say, where is Professor Dolby's office? Then I'm going to change that Dolby to bracket, look to see if there is that exact match in my database. If not, I'm going to look for the closest thing that there is. And then I'm going to now be like, this is the question. I know the answer because the answer is in this table. Now I'm going to take the actual word that they used, Professor Dolby or whatever it was, put it in the table, get the result, and that's how I answer it. Okay? There's also one more step maybe after that takes the result and puts it back into an English sentence, which I actually even asked the students to provide also the format of the answer. So every question is also going to have professor, bracket professor's office is in such and such place, like that. And so you can also mine that, just plug it in, and you get your answer back. Okay? Now, it's not as easy as it sounds. There's got to be lots of different ambiguities. Like I could just put in the word not in there. Looks very similar to another question that just doesn't have not in it. Statistically, it's very similar, but it's completely different because it has not. You know, you have to look at that separately and have a special case to handle things like that. Negation is a big part. I might be asking things you literally don't know about. And so what I want to see in that situation is like, I don't know. But if you just do the bare minimum of the statistical analysis and distance finding, you're gonna, the way it works in distances is that take an object, another object, find the numeric distance between them, and if you're not careful, you're gonna find a distance anyway, even if it's completely irrelevant. If I said like, what's the price of tea in China? It's gonna be closest to one thing I have, even though all of it is completely irrelevant. And so if all you're looking at is the closest distance, that's a problem. You need to figure out something more sophisticated. Is there a minimum distance that needs to be there before you even do it? And then you need to answer, I don't know the answer to that question, right? That's the correct response. But that's really hard too, because I could ask a relevant question and simply haven't seen the format for it before. You should be able to answer it, but you haven't seen the format, so it's gonna be hard to answer. One of the things you should be doing is when you take the question, you could expand it. In fact, not just the question. When you take the database exercise they had of time, like all of the 120 questions that everybody had to write, right? Which I'm going to hand over to you guys, right? You can artificially create more questions based on the questions that you already have, just by having words that are synonyms or similar, and then be like, oh, I can pretend like this one question could have been answered 8 or 9 different ways, and throw all that in there so that now I increase my chances of matching it. It's still gonna be the same answer, but it's like 6, 7 different ways of asking the same question. It's just, that's real life. Where's Professor Koshwood's office? Can you tell me Professor Koshwood's office? Do you know the location of Professor Koshwood's office? What part of the campus is Professor Koshwood's office? All that is the same thing, right? What you need to do is recognize that those are the same thing and give me the correct format of the response. And then once you figure out that, you formulate a native response, that is to say, you found the answer and you replied to it, or you formulate an intelligent non-native response, which means I know that I don't know the answer, and I'm going to respond to it as helpful as I can. Like, please call the department office. I don't know what this means, or look it up yourself, or something like that. Yeah.
You were talking about kind of like the kind of pragmatic, ambiguous way of saying like, it would be nice to meet with Dr. Cosmo.
Absolutely.
Would it be able to address that type of issue as well if you're able to label something like that?
Well, here you're not specifically recognizing the pragmatic discourse, okay? That would be very difficult. You could probably get down that road, and you probably have a year, you could probably do something nice with that. But a way to get past that problem is to simply put that in as another format of the same question. And so now, if you see, it would be nice if you could basically either dismiss that whole thing or just put in, it would be nice to, for every question, generate that, so that every question has a version of it that says it would be nice to, and then you would match. So as far as the machine is concerned, it's not pragmatic, it's just a word match. But then you don't have to actually recognize the pragmatism, which is very difficult. That's what I was saying, like when you would take the initial questions and kind of mutate them yourself. Now that's hard because sometimes you would generate non-grammatical things. So you have to be very careful how to mutate things. I can help with that. I've done that. That works somewhat before. It's a transform that you have to do, like English to English should be equivalent. Like I could say, maybe replaced with perhaps. Things like that. Yeah.
Would it be reasonable to add a training data generating step in the interface where, so if someone says, it would be nice if you told me Dr. Custer's office, and then it doesn't understand, or maybe it tries to answer afterward, there could be a question of, hey, was that right?
Absolutely.
Did you mean this, or this?
Yeah.
Or something else?
You're thinking right along the right lines, for sure. A couple things you can do on that. First of all, to continuously gather data, you need something at the end that says, was it right? That needs to happen. Like, whatever interface it is, please tell me if I'm right or something like that would be in there. Second, and this is somewhat more complicated, but and I'm not requiring my students to do it for my data mining class, but I feel like you guys should be able to do this. You have enough time, okay? Get into producing a discourse rather than just a question. In other words, ask the person's name, and then whatever questions they ask now is with the assumption that you know what they've asked before. For example, can you tell me a computer science professor who has office hours at 2 p.m.? Sorry, no computer science professors have office hours at 2 p.m. My next question, what about a stats professor? The what about a stats professor on its own is meaningless, but if you know that I asked the question before, you could actually address it. Much more natural, right? The key to that is that you have to have a session, which means that the same person is talking to the same bot. And in that session, you could start it by asking the person's name, and then it could be ended if the person stops responding for like 2 minutes, or the person types bye or something like that, and then you know it's ended. And within that session, you have contextual information, which is very useful, because now you can make more decisions based on questions that have been asked before. Otherwise, what you have is a question in a vacuum, and it doesn't really help you all that much. You don't know anything about the next question from the previous question. And then, if you do it that way, there's also cool things you can put in, like that makes it much more natural. Like, I just answered this question 5 times, why do you keep asking me the same thing? You know, stuff like that. That would be kind of cool. You can put in there. And secondly, within a context, one thing you could do is ask a question back to the user. Can you tell me a professor who has office hours at 2 p.m.? Do you mean statistics professor or computer science professor? Statistics professor, I type it in. And then, that helps make your job easier. What you don't want to do is ask many questions all the time, because that's just really tedious, Sure, you can actually get your query to be completely unambiguous if you just keep asking tens of questions from everybody. Like, do you mean this? No. Do you mean this? No. Do you mean this? Like that. But that would be great. That would be non-friendly. So don't ask a question if you don't have to, and if you do have to, ask as few as possible. Yeah.
So you're talking about the session. How does the system know? So if you were to ask a question about office hours at 12 p.m. in computer science and it doesn't know, and then you ask stats, how does it know that you're talking about office hours at 12 p.m. Later on within that session?
Well, within the same session, what you would have is, normally what is done is that there's going to be a object in memory that has that at the beginning has nothing, but then there's going to be some labels pretty soon, like I just asked a question about office hours in statistics department, okay? So in that object in memory, I would have office hours equals true, department equals statistics. And then next time, if I'm asking a question that is missing some parts, I'm just going to go back in that object and look up the last things that we were talking about and pretend like those were the parts that are missing. And then I could easily just drop in all the variables that are missing. Okay, that would be one way of doing it. Of course, it needs to be a little more massaged, so that maybe if I asked a question like 6 questions ago and now I'm going back to that, it can figure it out, or etc. So a little more logic to do that, but I feel like that's kind of a fun project to figure out. Yeah.
I was going to ask about decaying, so what you said.
Oh yeah, absolutely. It needs to have a relevance, because just like in real life, I could be starting to talk to something to you, and then like an hour from now, it wouldn't be reasonable for me to go back to something I said an hour ago and expect you to have that fresh in your memory. So yeah, you could have a decay factor. You could just have a hard limit, like only 5 or 6 things. That'll be fine. You could detect that a subject matter has changed, another machine learning problem, and only keep things for the subject matter. Do you want to go back talking about office hours now? Do you want to shift over and talk about professors now, like that, right? One of the biggest things at first is going to be the question which sub area it belongs to. Like, one very valid way to go approach this, to make it completely hierarchical and basically have lots of small bots. That's literally what I'm doing in the class. lots of small bots that are super specialized in their little area. Like somebody specialized in courses, somebody else is going to be specialized in like professors, all those things, right? All these different things. Every one of these things has 2 teams on it, right? And for you, the question becomes, well, I have these super specialized bots, which they more or less work the same way, but some of them might have some extra handling code and some, for example, this one, department info, hours, buildings, things like that. That's a little less structured. And things could be like in paragraph form when you go to that page. And so now you have to work a little harder, and you could put in like a few like conditional statements that make things easier just for that one, you know? But the other ones, for example, this one, majors, minors, that's like a table. You download the table, everything's very structured. So these bots could have peculiarities amongst themselves, even though they kind of use the same backend data with the labeled questions to learn from. And your job at first becomes which one of the microbots should actually answer the question. And that's a classification problem. And so you can do a 2-stage thing. First, you take the query and then say, all right, which one of these subject matter experts should actually answer it? And then the second thing is that subject matter experts answers the question, right? And at the beginning, you just have to make a decision between which area does it belong to. And that's a classification problem. You can run all kinds of things on neural nets or naive Bayes or anything like that. Here, I would remember all of the words that you scrape from the websites so that you can use them for context to say, like, this website has a lot more in common with this, and that website is about office hours, so I'm going to pretend like your question is about office hours, right? And then having the feedback and the ability to question back the user, you could validate if that was correct. Okay. I'll stop here. Later on in the fall quarter, if you guys are working on a specific problem, I'd be happy to come back and do something more specific. Like there's information retrieval methods that have the math of how to associate like one string with like a larger corpus and say like this belongs to this one or that one using like TF-IDF or like, you know, cosine distance and things like that we can get into if you want. Okay, any questions? All right, I'll send you the slides. You can send them on to the club members.
Thank you. Awesome. Thank you so much.
And so, if you're worried about the formatting changes,
Yes.
I think you could just look at the text in the page source, and that wouldn't change. But if you're worried about that, you can take a screenshot and save it with each section of data, and then compare screenshots between data captures, and look for the percentage when it's
I think it might be a little easier.
Oh yeah. Yeah, let's know. It has like a size of
So if you have div tags, so text the tags, they're just like wrappers. That way you can just insert text and say what's the text is pulling an image, so there would be like a bitmap.
Yeah, that's what I'm saying. It's probably a lot easier just look at the page source, not worry about the formatting, because you can use because you're talking about how people use the grid for food. I don't know, it does, okay.
Based on the size of the screen. So usually normally
Hey guys, so
you can shrink things.
we're going to take a quick moment to, each person is going to go up and briefly introduce themselves to Dr. Cosmoon. We'll start with Max, and then we'll go this way around to the back. So yeah, just come in really quickly and introduce yourself, your major, and yeah.
maybe what you're working on for this project if you have.
Hi.
Hi.
Good to meet you. Yeah, so I'm a first year, student here, and, full major, business major, John. Yeah, so, not like technical line, there's,
CSAI 101.
Or yeah, what's the name is you're gonna be. But should you take like
Yeah.
the whole
Yeah, I was really interested in this, I just wanted to.
Oh shit.
I'll go for like 4,
That's what all the signs.
So that was a really interesting time. I feel like we have a very clear path forward.
Yeah, it's feel the aerodynamics.
I saw this one AI.
Feel the energy rushing past, makes you feel more productive.
Not so much.
Grammatical analysis questions, like you could say
Yeah,
we get a
so
question.
maybe that's tomorrow.
The hat didn't fit in the suitcase because it was too big. What's too big? Right? What is it?
So the one land I have right now is very
Dude, you said
It's a statistical model.
situated
I think it does is it generates
format.
fake text questions.
Yeah.
So you can give like a beginning of a book with one sentence summary. And the length question is Wait, do you have a laptop? Mine's dead, yeah. I didn't Yeah, I'm gonna read that so I can choose myself.
Yeah, exactly. But I'm thinking something more first and then
I know, I'm doing that all the time. I was thinking that. Yeah, I didn't know. I was like, there was one that I need a process for. I literally had like, I kept messing it up, so I just checked. And it didn't write. But it's the exact same, so I was like, okay, it's the exact same answer. And then I couldn't figure out what was 10 minutes left because that's what I skipped before, right? So I went looking at the exact same value, the exact same value, I'm not sure if you're right, copy answer, and it works. I'm like,